Brilliant. All right. Well, thank you very much indeed for the invitation to speak. It's a pleasure to be here virtually. I thought I'd start by acknowledging all the people who've done the real work. This is in particular a collaboration with Martin Dove, who is a long-standing collaborator of mine and who's done a lot of thinking about these topics. And it comes out of work done by our students, Juan Guanchun and Zhongsheng, and Martin's own student, Lei. And I'd like to thank also, obviously, the funders and the instrument scientists at ISIS who helped us get the experimental data, which I'll present in a moment. Since I haven't done a TYC talk in some time, I thought I would give a quick introduction to the sorts of things I think about and the sorts of things I do. I am a crystallographer by training, and of course, crystallography was one of the very first serious applications of scientific computing in the UK and in the world. And as computing power has gotten better, we've been able to do more and more complicated experiments and more subtle experiments where you really need good simulations to back them up, to understand what the data are in fact telling you. So I'll give you some examples of this slide of the sorts of things I do. I guess it's no secret that that accurate DFT phonons have kind of revolutionized the interpretation of inelastic neutron spectra and made far more complicated materials viable for that technique. Then there are things like molecular dynamics traces, which you can take a double Fourier transform of and transform straight into a quasi-elastic scattering simulation. But actually, in today's talk, I'm on the left-handed to the sort of the toy end of the model sophistication spectra. So I'm going to be presenting a couple of very simple, what we call toy models, classical potential models, which are deliberately so. They're designed so that we can isolate the underlying physics behind a phenomenon. And in fact, I'm going to also present some reverse Monte Carlo modeling, which by design has no physics in it at all. And I'll explain at the time why that's a virtue rather than a vice. Briefly, it's because we don't have to have a preconceived model of what's going on in order to start our simulation, and therefore we're free from the bias that might introduce. So the plan is that I start by talking in general about what I mean by unexpected thermodynamic properties. And then I'm going to spend a second half of the talk talking about one particular material, scandium trifluoride. So you might ask, unexpected to whom? Well, unexpected to Lavoisier. Lavoisier started his famous elementary treatise on chemistry by saying, basically, if you heat anything up, it always expands. And of course, we now know that's not true. There are materials with negative coefficients of thermal expansion. So NTE, negative thermal expansion, is my first unexpected thermodynamic property. Of course, Lavoisier wasn't entirely wrong in the sense that all individual chemical bonds do expand with temperature. And the reason for that's very simple. The limit of the potential as you push the atoms together goes off to positive infinity. The limit as you pull them apart goes off to zero. Somewhere in between, you've got a minimum. And therefore, intrinsically, there's an anharmonicity, which means the average position of the atom increases as you give energy to that particular vibrational mode. Of course, if this were a harmonic oscillator, there wouldn't be any thermal expansion at all. So the first of three key ideas I'm going to introduce in this first section is that anharmonicity is important. There are three little bits of received wisdom, if you like. I'm going to come back to them in my conclusions and modify these ideas very slightly. But for the time being, anharmonicity is important. The fact that individual bonds expand with temperature, of course, doesn't mean that all materials expand with temperature. And there's a very simple, intuitive explanation for that that's come to be known by the tension effect. In other words, if I have a chain of atoms here, two atoms in the end in green and atoms in the middle in red, if the red atoms, if the intermediate atoms vibrate transverse to the chain length, then the two ends of the chain are drawn closer together, a bit like a skipping rope, and you end up with negative thermal expansion. There's an alternative way of looking at this through the Maxwell equation on the right hand, or the Maxwell relation on the right hand edge of the screen, and that's that the thermal expansion is related to the change in entropy as the change in entropy as you change the volume. So if you have a material like this simple example where you can increase the entropy by crumpling it up by decreasing the volume, you might expect that material to have a negative coefficient of thermal expansion. And that gives rise to the question, do longer change of atoms lead to more flexibility? it turns out that there's perhaps a slightly better way of looking at that, and that's to take a reciprocal space view rather than a real space one. And that shows you that longer chains mean that there are more wave vectors which are acceptable in the sense that they're low frequency enough to make substantial contributions to the thermal expansion. And this is one of the key ideas of Martin's, which is become quite well known, the idea of a rigid unit mode. So if you have a vibrational mode that leaves coordination polyhedra undistorted, that's likely to have a low frequency and therefore to be relatively easy to populate thermally. And the key difference between our single atom linker and our polyatomic chain linker is that if I have a single atom linking my coordination polyhedra, like the top of that diagram, then those modes can only occur at very, very specific wave vectors. In this 2D case, it's a half. Whereas if we have a polyatomic linker like we do in the bottom diagram, then I can have that rigid unit mode anywhere I like in the Brillouin zone. So there's much more about this idea in two excellent reviews that Martin's written recently, the top one on NTE, the bottom one on the rigid unit mode model. But for now, second key idea is that these rigid unit modes turn out to be important in anomalous thermodynamic properties. The first time I got involved with this work was 12 years ago now, when I was a member of Cameron Cappett's group in Sydney. And that was on this material, cadmium cyanide. Normally this crystallizes, as it's shown on the left, into interpenetrating networks. And each of those bars there, I've shown it's just a simple cartoon model, but each of those bars is a cadmium, carbon, nitrogen, cadmium chain. So it's like those diatomic linkers I showed in the previous slide. If you grow this thing, however, in a carbon tetrachloride atmosphere, then it turns out that blocks one of those networks from forming, and you get a single network of cadmium cyanide with carbon tetrachloride in the pores. And you can then heat it up and remove the carbon tetrachloride from the pores, and you end up with a material that's just single network cadmium cyanide. It's cadmium cyanide but half the density. And you might expect, if this transverse motion is so important to the negative thermal expansion, maybe removing that second network would allow more transverse motion and therefore increase the NTE. And that seems to be the case, in fact. So this gave a negative thermal expansion material that contracts isotropically when you heat it up. And in fact, at the time, it was the record holder. It was the biggest known negative isotropic coefficient of thermal expansion. It's about 3 times it contracts by about 3 times the amount that steel expands when it's heated. It's no longer the record holder. It lasted about 1.5 years, I think, but never mind. But that brings me to this third idea, which was quite popular in some of the work that Cameron was doing at the time, that not blocking these transverse vibrations is important. If you can somehow stick in guests that block those vibrations, then you're likely to drive it towards positive thermal expansion. Okay, so that's thermal expansion. I promised thermodynamic properties plural, so let me talk about another one now. Martin, in work with his student Hong Fang, realized that actually the same modes that give rise to negative thermal expansion also give rise to pressure-induced softening. And so to be quantitative about it, I guess I'm talking about the pressure derivative for the bulk modulus, as shown there on the right. If a material buckles under pressure, then you might imagine that it becomes easier to squash. So the transverse motion that causes a negative thermal expansion should also cause this decrease in the bulk modulus. And again, that's an anomalous property, because you'd normally expect materials to become harder to squash, to exhibit more resistance to squashing as you increase the pressure. I should point out at this point, this isn't just a curiosity. So obviously, there is a real question of fundamental physics here, which is, what is the link between the mechanical properties at the atomic and at the macroscopic scales? Can we engineer linkages of atoms in such a way to give the thermodynamic properties at the macroscopic scale that we want? But there's also a very serious practical question here. Thermal expansion is something that you have to take into account when you design things. Sometimes you can take that into account at the actual engineering level, as shown in the top row there. This is my excuse to give a picture of the Sydney Harbour Bridge, but you may or may not know that there are hinges at either end to accommodate the thermal expansion, because Sydney summers are pretty hot and it does get bigger in summer. But the bottom two pictures there are examples where you really want to solve a problem at the materials level. So if you have, for instance, in your stove, the glass coating, the glass covering, that has to be stable and not crack, regardless of whether the stove is on or off. So that's hundreds of Kelvin difference. And if you want to do that, then you need perhaps to have a composite that combines negative and positive thermal expansion materials. But if you take a composite and you heat it up, then you're going to cause internal strain. And if the negative thermal expansion materials respond to that strain in another anomalous way because of pressure-induced softening, you can start seeing that there are some quite complex and interesting interactions potentially between all of these properties. A more exotic example is the use in spacecraft, because the difference in temperature between the side facing the sun and the side facing away from the sun could be thousands of Kelvin. So Martin and I took this idea of negative thermal expansion being related to pressure-induced softening and started building some of these simple one-dimensional toy models I was talking about. And I'm not going to go into detail here. This is the work of Hongfang at Cambridge. But you can see very briefly on the right-hand side that we were able to show that these models do give rise to negative thermal expansions, negative alpha values in the top row, and to pressure-induced softening, that's negative B prime in the bottom row. Okay, so that was a bit of a whistle-stop introduction, but that's all we had time for. Let me get on now to the specific material that I want to talk about today, which is scandium trifluoride. So that's the crystal structure there. It's what's known as a vacancy perovskite. So the very famous perovskite structure is there on the left. If you take out the A site cation, you end up with this structure in the middle. Scandium trifluoride, rhenium trioxide, and a number of other inorganic and hybrid materials have this structure. In fact, there's quite a nice review that Tony Cheetham and his group recently wrote there on reference in the bottom of the screen. And this struck us as a nice example, partly because it's known to exhibit NTE, and partly because it's such a simple sort of intuitive structure. I mean, it's kind of the 3D analog of the diatomic chain of the sort that I showed before, the sort of toy model we were playing with. One of the further interesting things that have been pointed out about this material from DFT calculations was that some of the key modes, like this one illustrated on the right, it's at the R point in reciprocal space. If you follow them in a sort of independent mode approximation, you discover that they're quite strongly anharmonic. So you need a quartic term to make sense of them. And this is kind of what you might expect from a rigid unit mode perspective. It's really it's quite easy to excite this mode. So you might expect you have a very low harmonic term, and then higher order terms start becoming important. But the theory was that this anharmonicity was vital to the negative thermal expansion behavior of this material. So we went away and we did some experiment. We measured the pair distribution function of this material. On the left, you can see the literature data, just showing the cell parameter and the coefficient of thermal expansion. And you can see that at low temperatures below about 800 Kelvin, this material is indeed negative thermal expansion. In the middle, you can see the pair distribution function. That's just a histogram of interatomic distances, and it's particularly easy to interpret in a case as simple as this, because each peak just corresponds to atoms that are that distance apart. So you can see from the structure in the top right-hand corner, the closest atoms are the scandium and fluoride pairs, and that's the first peak there at about just above 2 angstroms. The next pair of atoms are the fluoride to fluoride across a diagonal, and that's the next peak, and so on and so forth. So you can see this gives a snapshot of the local structure of this material. And just from that pair distribution function, we can quite easily follow the thermal expansion behavior. And as shown on the right-hand side, the scandium to fluorine distance actually increases. The individual chemical bond grows with temperature, as I said on my first slide. But despite that, because of this transverse motion, the scandium to scandium distance, or almost equivalently, the unit cell size, decreases with temperature. But we wanted to do a little bit more, so we went off and did some reverse Monte Carlo modeling. I'm not going to go into detail about how this works, but very simply, the idea is just to take a box of atoms and shake it up until it agrees with the neutron scattering data. And if we put in data that are sensitive to both the long range and the local structure, then we get out an atomistic configuration, which is consistent with our experiment. This is the one that I said that deliberately it doesn't have physics in it. We want to allow our model to reflect whatever the experiment is telling us. However, we do know from doing this that our model is going to be consistent with some configuration of atoms. So it's not entirely unsophisticated. And in fact, it's better for that reason than simply integrating under a single peak of a PDF, which could give you a result which is not actually consistent with any realizable configuration of atoms. That's something that we're having something of an argument with over another group, with another group over the exact interpretation of the PDF, but I'm not going to go into details there. So we end up with our configuration, our big box of atoms, and we can start interrogating that for interesting behavior. So we can, for instance, decompose our configuration into the ways in which those scandium fluorine 6 coordination octahedra distort. And we find that a really quite large percentage of the motion, about 70% of the distortion, comes from bond bending within those octahedra. We made a little toy model again to simulate this. So I'm talking about the bending associated with the angle theta in the top right-hand corner. And the nice thing about a toy model is you can just twiddle the knobs and see what happens. So we changed that bending force constant to see what percentage of the motion could be represented as bond bending, octahedral rotation, or bond stretching. And I've superposed that with some experimental data. And you can see on the right-hand side, we have a well-known traditional perovskite, strontium titanate, with quite a large bending force constant. Somewhere in the middle, we have cesium lead iodide. And right at the left-hand side, we have scandium trifluoride with a quite little resistance to octahedral distortion. And you might say, well, maybe that's that proves that RUMs don't exist in this system. But that's not quite true either. If you look at the phonons from our toy model and compare them with DFT, you can see we actually get quite good agreement. That's not a coincidence. We chose our parameters to match the DFT. But in particular, we still have these very, very low frequency vibrations along the M to R line, and those are our RUMs. So it's not that we're losing our rummy behavior, it's just that the rummy behavior is spilling over into neighboring parts of the Brillouin zone. And that's important because if you think about it, our total atomic displacement is going to be integrating over phonons from all the Brillouin zone. So the more contributions to negative thermal expansion we have from everywhere in the Brillouin zone, the better. If we have a beautiful NTE mode that only exists at a special point, it's not in itself going to be able to influence the thermal expansion enough. The second interesting point about this is that the transverse motion is not necessarily anharmonic. So here I've just plotted the transverse displacement of the fluoride atoms. And you can see we at every temperature, we get a beautiful Gaussian fit. And more than that, the width of that Gaussian goes up beautifully linearly with temperature. So I'm not repudiating the previously published DFT results. It's not that mode isn't quartic. It's just that mode is a single mode. And when you do integrate over the Brillouin zone, it turns out that the atom's behavior can be described rather well in the harmonic approximation. And in fact, this transverse motion isn't even the most important motion to describe the NTE. So again, I've plotted here what happens when we twiddle the knobs in our toy model to change those bending force constants. And the red lines there show our best fit values to the actual experimental data. And you can see if we wanted to change that angle theta, the bond bending one, we need to multiply by about 3 to stop the negative thermal expansion. And if we wanted to change the phi value, though, the one that you might associate with transverse motion, you need to increase it by a factor of 40. And we know that in positive thermal expansion materials like strontium titanate, that bond bending is nowhere near 40 times as much. In fact, it's a soft mode, so it goes to 0. So in fact, it is the theta angle, the octahedral distortion parameter, which is the most important in controlling the negative thermal expansion in this material. Okay, in the last couple of minutes, I just wanted to move on from thermal expansion and go back to pressure-induced softening. If you run our toy model and look for pressure-induced softening, this is what you get. you get negative B prime. And we thought that was interesting. We thought, let's go and test it. So we took it off to ISIS. On the left is how we expect the pressure volume curve to be from the toy model. You can see it's concave slightly down. It's curving downwards, that pressure-induced softening. And on the right is our experimental data from ISIS, and you can see it's curving down even more. In other words, the pressure-induced softening is more than we expected from our simple toy model. How much more? Well, you do the calculation, and you find you get down to minus 200 or even slightly more. So that's a negative B prime, an order of magnitude greater than has previously been reported. Just for context, the standard, most materials, normal would be 4, positive 4. So minus 200 is really quite an extraordinary value there. Okay, I'm running out of time, so let me return to conclude to my 3 key ideas that I brought in at the beginning. I said anharmonicity is important. It is important, but the presence of some anharmonic modes, like the quartic modes in scandium trifluoride, is still consistent with overall harmonic atomic behavior. So we shouldn't get too excited about individual modes being strongly anharmonic. Second key idea is that rigid unit modes, RUMs, are important. And they are important. But it's also important that the polyhedra are able to distort slightly. And the reason for that is that it allows the negative thermal expansion behavior to spill over into more of the Brillouin zone, so it can actually have a substantial effect on the thermal expansion. And the third key idea is that not blocking these transverse vibrations is important. And again, that's still true, but it's still true that you can put in guests or take them out to influence thermal expansion behavior in many materials. But it turns out from our toy models that actually the guest's effect may be most important in changing the polyhedral distortion rather than blocking the transverse vibrations per se. So if you want to read more about this, half of this has just been published in PRL. The other half we hope to be in the published literature very, very soon, but for now it's on the archive. Thank you for your attention. I'd be happy to answer questions.